Hi everyone. In today's video we're going to keep talking about how we calculate the value of a limit exactly if we're given a function. So if you'll remember, what we've been working on so far is determining limits using algebraic manipulation. And we had a few strategies there we could use to calculate the value of a limit exactly. So the first thing we always tried was to calculate the value of a limit algebraically using substitution. So for some of our functions, we were able to just plug in the value and then get the limit value out. However, sometimes that didn't work, so we had to use other methods. So we could calculate the value of a limit that requires algebraic manipulations, such as factoring, multiplying by a conjugate, or eliminating fractions. And then usually once we tried one of those methods, then we could go back, substitute, and get the value of the limit. But what we're going to be talking about today is what to do if none of those strategies work. And just to reference back to our learning targets, this is going to be really working with the targets around 1.14 and 1.15. So connecting infinite limits and vertical asymptotes, and then connecting limits at infinity and horizontal asymptotes. So again, it'd be worth it to run through those targets. That's really the material we're going to be talking about today. So I'm going to make a note here. This is 1.14 and 1.15 in terms of your learning targets. So again, the idea is that what do we do if none of those algebraic strategies work for us? So if none of our algebraic techniques for determining the value of a limit are successful, then the graph must have a vertical asymptote. At that x value. Okay, so in this section, we're going to kind of talk about these targets here, identifying the locations, if any, of the vertical asymptotes of a function, and then analyzing the behavior of a function excuse me, near a vertical asymptote to determine the value of a limit. So when we're analyzing vertical asymptotes symbolically or algebraically, the important thing here to really make sure we understand is that only rational functions can have vertical asymptotes. And when we talk about rational functions, we mean functions like this that are written as a function, or as a fraction. That's a rational function. So a rational function will have a vertical asymptote at x values that make the denominator equal to 0. So for example, we could be asked this question: determine the location of the vertical asymptotes of the following function. So we said those are going to happen where our denominator here is equal to 0. So we're going to go ahead and solve this equation. Now here I've got a quadratic trinomial, so I'm going to go ahead and try to factor that. So this one looks like it factors nicely into x plus 2 times x plus 1 is equal to 0. So that means x plus 2 equals 0 or x plus 1 equals 0. So I have vertical asymptotes at x equals negative 2 and x equals negative 1. So again, we find those just by setting that denominator equal to 0. Now, when we're analyzing this graphically, right, when a function has a vertical asymptote, the y values of the function are forced towards either infinity or negative infinity. And we looked at this earlier in the chapter. We said vertical asymptotes are the things that force those y values to infinity or negative infinity. Therefore, when you estimate a limit at the location of a vertical asymptote, the limit value will always be infinity or negative infinity. So in our example here, I have a vertical asymptote at x equals 0. As I approach, again, if this is 0, here's the left side of 0. As I approach from the left side, if I follow my curve, I'm heading down towards negative infinity. On the other hand, from the right side of 0, as I follow my curve, you can see I head up towards positive infinity. Now that part isn't new. The part that's new is how are we going to find these limit values when we're not given a graph but a function. So let's go ahead and turn the page and look at a few examples. So this asks us to determine the value of the following limits using algebraic techniques. So here's how this is going to look. Now, when I see a rational function, right, I'm looking at it, I see that it's a rational function. It's written as a fraction. The first thing I'm going to think about is where any vertical asymptotes might be. What's going to make this denominator equal to 0? So in my case, I know that there's a vertical asymptote. I know there's a vertical asymptote at x equals -2, because if I were to substitute -2 into here, I would get 0. Once I know there's a vertical asymptote at -2, and I see that's where I'm evaluating my limit, I know my limit must be either positive or negative infinity, because I have a vertical asymptote and that's the same value where I'm evaluating the limit. And so we're going to use that information to just do a little kind of algebraic analysis. So here's what we want to do. I'm evaluating at -2, so I know my limit has to either be positive or negative infinity. So now, when I'm thinking about -2 from the left side, I'm thinking of a number like -2.001. So let's think about what would happen if I substitute that in here. I would have a positive number, that 3 is positive, over, let's see, -2.001 plus 2 is going to give me a very small negative number. But when I raise that to the 4th power, that's going to give me a very small positive number. So I know now my answer, if I have a positive over a positive, that has to be positive, so my limit must be positive infinity. Remember, my only two choices were positive or negative infinity. Now, on the other hand, if I'm looking at the limit as x approaches -2 from the right, now I'm looking at something like -1.999, let's say. So let's do our same analysis. My 3 on top is still positive. On the bottom, let's see, -1.999 plus 2. Well, that's going to give me a positive number, and when I raise it to the 4th, it's going to stay positive. It's going to be really small, but it's going to be positive. So now I have a positive over a positive, which is going to give me positive infinity. So now, since my left and right side limits are both positive infinity, I know that two-sided limit is also positive infinity. So this is the analysis we need to be able to do kind of in our heads, but I do think it's worth checking the graph to make sure we've got this right. So let's go ahead and enter this, confirm with the graph. So 3 over the quantity x plus 2 to the 4th power. I'm going to graph that. You can see the asymptote there, and from both sides we're approaching positive infinity, so that matches with our analysis. All right, let's look at this one. So now I've got -5 over x minus 1 to the 5th. So when I'm looking at my denominator, again, I'm focusing down here. I know that there's going to be a vertical asymptote at x equals 1. And again, when I look here, I see, well, I'm evaluating all of these limits at x equals 1, so the limit must be positive or negative infinity, because that asymptote is going to force that kind of behavior. So let's take a look. Again, we can do some analysis here. If I approach 1 from the left-hand side, I'm looking at something like 0.999, let's say. To the left of 1 might be 0.999. So now, on top, my numerator this time is a negative number. If I do 0.999 minus 1, I'm going to get a negative number. When I raise that to the 5th power, it's still going to stay a negative. It's going to be a small negative number. So now I have a negative over a negative is a positive. So this has to be now positive infinity. My choices were positive or negative infinity. So since I have a negative over a negative, it has to be positive. Now, 1 from the right is going to be something like 1.001. So when I look here, negative on top, on the bottom, 1.001 minus 1 is going to be a positive number. When I raise that to the 5th, it's still going to be a positive number. So now negative divided by positive, this one has to be negative infinity. So in this case, for my two-sided limit, we would say that does not exist because the limit as x approaches 1 from the left of f of x is not equal to the limit as x approaches 1 from the right of f of x. And again, I think it's worth taking a look at the graph to verify, especially while we're just getting familiar with this. So let's see, from the left-hand side, I can see that I'm going up to positive infinity. If I approach from the right-hand side, it's negative infinity, so we can validate our answer that way. Now, one thing I really want to make sure we're clear at is this whole idea of the limit being positive or negative infinity is only when we're evaluating at the limit where we know there's a vertical asymptote. We don't want to overgeneralize this. So for example, I'm just going to make up a question. Let's look at this. If this happened to say the limit as x approaches, let's say positive 2 of f of x, well now the value I'm evaluating it at is not where the vertical asymptote is. So now we would just plug it in. We would do 3 over 2 plus 2 to the 4th power, which would give us, let's see, 4 to the 4th would give us 256. So make sure this idea of positive, negative infinity is only when the value where we're evaluating the limit is the same value where that vertical asymptote occurs. Okay. We're going to skip this next part because we'll talk about that in class. Let's look at our big idea number 2. Now, this is really asking how do we plug in positive or negative infinity? So normally our first strategy when evaluating limits algebraically is to try to substitute the x value into the given functions. However, in situations when x is approaching either positive or negative infinity, we need to rethink our substitution process because infinity is not a concrete number. It's not something we could just plug in. So when we evaluate limits as x approaches positive or negative infinity, we're really examining the horizontal asymptotes of the function. And we've talked about that a lot when we've been looking at graphs. We said those horizontal asymptotes are really what control the behavior at the far ends of the graph. So here's our learning targets for this. We need to be able to identify the locations of the horizontal asymptotes of a function, determine the end behavior of a function using algebraic or graphical methods, and then using the end behavior of a function to find the limit of a function as it approaches infinity. So here's kind of the old stuff. We started off being able to determine these limits or end behavior graphically. So as we look towards positive infinity, right, I wanted to know what was happening at those far ends of the graph here. We can see we're approaching this horizontal asymptote at 1. So we're approaching 1 when we get to the far ends there. Now at negative infinity, that's back here. What happens when the numbers get really large in the negative direction? Again, I'm approaching that asymptote, so my limit's still 1. Now for this graph, as x approaches infinity, as it gets really, really large, you can see my y values are just going to keep getting large in the positive direction. So that's positive infinity. And then when I approach negative infinity, my y values now are getting really large in the negative direction. So that's negative infinity. So graphically, I think we had a pretty good grasp, and based on our quizzes, we had a good grasp of what's happening. But now we have to be able to determine this algebraically. So since infinity and negative infinity are very large numbers, we only need to examine the highest powers of the function when evaluating, because those highest powers are what's going to take over when the x values get really big. So here's what we mean by that. Let's say I have this function f of x. When I look at the highest powers, I'm really considering my 5x to the 6th in the numerator and 3x to the 7th in the denominator. So when we talk about the end behavior model, we're really talking about looking at just those highest powers. So 5x to the 6th over 3x to the 7th. Now if I simplify this, I get really 5 over 3x. Now, here's what we need to know. This graph is really, we could write this as 5/3 times 1 over x. So really, this is what I'm concerned with. What does the behavior of 1 over x look like? And I know 1 over x looks something like this. So now I can use that end behavior to determine this limit. As x approaches infinity, I can see out here my limit is going to be 0. Same thing here, as x approaches negative infinity, my limit's going to be 0. But again, that was all controlled just by these highest powers. So now our note here says it's important to note that if the value of the limit as x approaches either positive or negative infinity is a number, so let's say you look at the limit and you get 2, the function must have a horizontal asymptote at that value. So for example, if I know the limit as x approaches infinity is 0, and I know the limit as x approaches negative infinity is 0, that tells me this function has a horizontal asymptote at x equals 0. Okay, let's flip here. We'll do a few more examples. All right, so now we're asked to determine the values of the following limits. So again, we're looking for that end behavior model, the highest powers. So I have 5x to the 8th, and then here I have to be careful. It's actually my 8x to the 6th here. So my end behavior model is f of x equals 5x to the 8th over 8x to the 6th. And so really what we have is 5/8 x squared. So again, what I want to focus on here really is this x squared. I know that a function with x squared is going to look like this. Once I've got that end behavior model, then I can clearly see as x approaches infinity, my y values are getting infinitely large in the positive direction. Same thing for negative infinity. As my x values get really big in the negative direction, my y values do the same. So my limit's positive infinity. All right, let's actually end that here. I think it'll be good to have a few examples to go through in class just to clarify any questions. So please make sure you've got all those notes. Make sure you've noted any problems where you had questions, and we'll take a few minutes when we get into class to kind of clarify anything that has come up and do these extra problems. Thanks, and I'll see you back in class.